All right, how is everyone doing today? Good? Excited for Thanksgiving? Yeah, me too. I'm gonna eat so much food. I'm so pumped. All right, does anyone have any questions before we get started? All right, cool. Then let's just roll right back into it. So we left off looking at this Diels-Alder reaction. So we said the Diels-Alder reaction was really an important reaction because it was making this six-membered ring from my diene and my dienophile. So the diene is the one that has the two alkenes. Then the dienophile is the one that loves the two alkenes. Our mechanism is this cyclization, so that it was still, we're starting at the pi bond of the nucleophile, of the thing that's electron rich. We're still starting there, and then going to our electrophile. That dienophile is the electrophile. But now it's just that we're gonna go in this ring. We're gonna have all the electrons just kind of like cycle around to form the ring. Our transition state has all of these partial bonds all the way around in the ring, so that we end up with this cyclohexene. So you have the double bond there, and we mapped our carbons on, showing that these were the new bonds that were being mated. Being made. So that we have that new alkene formed between the original carbons 2 and 3 of our diene, right? So that we know that wherever you see that alkene, if you go to, one away on either side, that was your original diene, right? That's that indicator that that's the bond connections that we're seeing. All right, so that was everything that we had kind of like started to lay out just for the initial bond connections, mapping things on. And right at the very end, we started talking about our electronics of our Diels-Alder and how to make the reaction faster. And we said that it'll be faster if I make my nucleophile, the thing that's electron rich, even more electron rich by adding electron donating groups onto that diene. That's going to make it more electron rich, therefore faster. For the dienophile, because it's our electrophile, we'd wanted to make it electron poor or electron deficient. So in order to do that, we need to pull electron density away from that pi bond. And we did that by adding electron withdrawing groups. And so we left off saying that these are the examples of electron donating, electron withdrawing groups, but I want to illustrate how we're actually seeing the donation or not. So induction, remember that is the delocalization of electron density through sigma bonds. So it's going to be through those sigma bonds. Resonance is through those unhybridized p orbitals, right, through the pi bonds. So when we look at our electron donating groups, if I imagine that I have this R group on there, that is going to be pushing electron density in, right? So it is donating electron density through that sigma bond. So it's pushing electron density into the diene, into the nucleophile. And so then that's what's helping make it more electron rich. And then we get these partial charges, where they're alternating because opposites attract. So we're pushing electron density really towards that carbon, and then we see this alternating charges. That's when we're doing electron donating groups via induction. So it's just through the sigma bond, and it's just pushing as much electron density right where it's attached. When we're looking at via resonance, for resonance, we want to look at resonance structures. So I told you that whenever you see this lone pair right outside your pi system, that is going to be your electron donating group. So that lone pair right outside the pi system is going to be the electron donating group, because when I draw my resonance structures, I have a lone pair next to a double bond. So I can start at the lone pair, push towards the double bond, and I get a series of resonance structures. So whenever you see this negative charge in that diene system, right, where you get the negative charge on one of the carbons that is going to be a part of that diene, a part of that nucleophile system, then that is electron donating because you get a negative charge on it. So that's making it more electron rich on the nucleophilic sites. So electron donating groups will either get the partial negative or a full negative on those nucleophilic carbons, on one of the carbons that's making the new bond. Our electron withdrawing groups are going to be things that are either highly electronegative, like the CF3, or our halogens, things that aren't going to be as stable, forming multiple bonds. So oxygen wants 2 bonds, but it can make 3 bonds. We've seen that a lot. It becomes a good leaving group, or our carbonyls can be protonated. Like we end up where oxygen can make multiple bonds and be okay. Our halogens, they really just want 1 bond. So they're not going to be electron donating groups because they're not going to be as stable having multiple bonds. So when we think about the electron withdrawing groups, if I think about it for my diene, that is pulling electron density away, so then this is going to make that slower because it's less electron rich or less nucleophilic. However, if I think about like having that CF3 or one of the other electron withdrawing groups on my electrophile, now having that dipole pull away is beneficial. Because I want it to be more of a positive charge. So if I want more of a positive charge, then I want the electrons to be pulled away from that pi system. So having something like a CF3 is going to now make the dienophile react faster. So our halogens and something like a CF3 group, those are our electron withdrawing groups. I can also have, via induction, so I can also have an electron withdrawing group via resonance. So something like this might initially look like it was going to be the diene because we see the 2 pi bonds, right? Like you see the 2 pi bonds. The difference is I have an oxygen. So it's not 2 alkenes, so it's not a diene, right? If I had 4 carbons, then it would be a diene because then it would be 2 alkenes. So it's not a diene. Instead, it is a dienophile that's going to react really quickly because via resonance, I can see that I can pull the electron density away from that alkene, away from that reactive site, making it even more reactive. So here, I'm getting a formal positive on those 2 carbons. Like we're just looking at the carbons that are either going to be the dienophile, or sorry, either going to be the nucleophile or the electrophile in the Diels-Alder. So we're looking at those 6 carbons and really just the ones that are going to form the new bonds. So the end ones. So we're looking like here and here, right? Those are the sites that we're looking for, where we're trying to find the partial positive, a full positive, the partial negative or a full negative in order to look at that inherent reactivity. So this is an electron withdrawing group via resonance, because when I draw the resonance structure, I get a full positive charge on one of the carbons that is going to be one of the new carbon-carbon bonds that's going to form the new bond. Does that make sense? Okay, it might make more sense then when we look at an example. So at the moment, just acknowledge that induction donating groups are just normal R groups. Anything that's just a straight up hydrocarbon. So your methyl, ethyl, even it could be like a phenyl or just anything that's a hydrocarbon, that'll be a donating group. That'll push electron density in. Anything that is highly electronegative that can't readily form double bonds, doesn't readily form the resonance structures, that's gonna pull electron density away. If I get the lone pair right next to the pi bond, that pushes in, electron donates via resonance. If I have a pi bond connected to an electronegative atom, that's an electron withdrawing group via resonance. Because we're always just looking at where are the resonance structures and looking at the carbons that form the new bonds. Okay. All right, so we're gonna practice. We want to try to find our new bond connections that we're making. So when I do something like this, I need to start out by identifying what is going to be my diene, what's going to be my dienophile. So is the structure on the left or the right going to be my diene? Left. So why left? Don't overthink it. So you're making it way more complicated. It's even simpler than that. Well, yeah, okay, it's important that it's conjugated, but it's like we've two alkenes, right? Like remember diene just means two alkenes. You're absolutely right, it does need to be conjugated, so that is a very important factor. But like when you're trying to pick the diene, you're looking for the two alkenes, right? If you see two alkenes, dope, that's your diene, because that's what a diene is, right? It's not like an extra special term. It's like a normal IUPAC, there are two alkenes. All right, so then what does that make my alkyne? If it's not the diene, it's the dienophile. It's gonna be the diene lover. So then when we go to show our arrows, we're going to start at the diene and push towards the dienophile, showing that we're gonna make that carbon-carbon bond. So to show that we're gonna make a bond, you have to end pointing at an atom, right? So we start at the pi bond and then point to the carbon, because that's showing that we're gonna make a new bond, making a carbon-carbon bond. So then because this carbon cannot have more than 4 bonds, I need to take this pi bond and push it away, and it's going to attack the other side of the diene. So then I'm going from, again, pi bond to atom to show that I'm making that new carbon-carbon bond. And then lastly, this carbon also can't have more than 4 bonds. So I need to push this pi bond away, and it goes to the middle. So it goes in between those 2 carbons. So go ahead and draw the product of those arrows. It helps if you number your carbons. And then try to name that thing. All right, what product did we get? You can also describe it if you're not sure of the name. Even if you are sure of the name, you can still describe it. What's up? Yeah. So it's going to be a 6-membered ring with our 2 alkenes. So if I number these carbons, and it doesn't actually matter where you start, because these aren't going to be like IUPAC numbers. These are just, I'm keeping track of all my elements numbers, right? So I'm just trying to make sure that I make the right bond connections. So I recognize this has to be a 6-membered ring because I have 6 carbons that are going to cyclize, and that's what the Diels-Alder does. It makes 6-membered rings. So I need to make a carbon-carbon single bond between C1 and C6. That's a G, 6. I need to make a single bond between C4 and C5 as I've drawn them, as I numbered my carbons. If you number them differently, then your numbers might be slightly different. And then I'm going to make a carbon-carbon double bond between C2 and C3. Everything else will stay the same, right? Or I guess I should also illustrate that I'm breaking. I'm going to break the double bond between C1 and C2, break the double bond between C3 and C4, and I'm going to break that alkyne pi bond from C5 and C6. Right, so I start out, I just draw my 6-membered ring because I know that that's how many carbons I need in the ring, so I'm just going to start there. Then I'm going to number my carbons so that I can keep track of where I need everything to go. So I made the new bond between 1 and 6. I made the new carbon bond between 4 and 5. And then I need the new pi bond between 2 and 3. So I get that alkene in here. So the thing that's missing is exactly as you had indicated. Having that C5, C6 pi bond, that is still there. I only took one of the pi bonds. So that other double bond just comes along for the ride. So if we went to name this, our actual IUPAC numbering would be you would start at one of the double bonds because you want to give your functional groups the lowest numbers possible. And then you just need to make sure you number going through the alkene. So because it's symmetrical, it doesn't actually matter which one we start on. So I'm just going to start on the left side. So I get cyclohexa because it's a ring of 6 carbons. And then my double bonds are starting at 1 and 4. And it's a diene because there are 2 alkenes. So it's cyclohexa 1,4-diene. Or 1,4-cyclohexadiene if you're using the old naming convention. So main thing with the numbering is make sure you always number through the double bond, right? If you pick number 1, that's indicating that carbons 1 and 2 have a double bond between them. All right, cool. Does that process make sense? All right, go ahead and try the next one. Did you get one of those two products that I drew? Okay. Only one of them is correct. So the important thing is if you drew one of them, then that's the first hurdle. You at least recognize we got to make the 6-membered ring. That's the first important, very important step. The next thing that we need to do is consider our electronics. So we need to identify our most nucleophilic site, our most electrophilic site, and make them match. So to know which one is correct, try to do that either the partial charges if it's induction, or draw the resonance structure to see the formal positive or negative, to identify our most nucleophilic and most electrophilic site, to know which bond connection you need. So try to prove to yourselves which one is going to be correct. Only one of them is correct. And then also go ahead and talk to those around you to see if you can agree. Like see if you can explain it to each other why, which one, or rather which one is correct and then why it's correct. And if you're not sure, it's okay, still talk it out. Like now is the time to be wrong. Like it's totally okay. It's just to make sure that we're understanding what's going on. So what I really love is I saw a lot of people do like a flipping thing, because that's absolutely right. We do need to flip our dienophile, because when we look at this R group, how do we describe this R group? Electron donating or electron withdrawing? Electron donating. And so that was an electron donating group. Was it via resonance or induction? Induction. So that means that we're just imagining that dipole pushing in. And remember, induction is a weaker force. So it doesn't go as far as resonance can go. So that puts my partial negative right on that first carbon. And then you get your alternating charges throughout because opposite charges attract. So that means my most nucleophilic site is this first carbon. If I imagine, well, actually, hang on, sorry. So this is my diene. This is my dienophile. Oh, did everyone get that? Did you recognize the diene versus dienophile? Sorry, I like really quickly skipped over that. Okay. So diene, because I see the two alkenes. Dienophile, because it doesn't have two alkenes. It does have two pi bonds, but it's not two alkenes. So we're going to have, that's my diene. This is my dienophile. Also, I know that it's going to be that way because this has an electron donating group, making my diene more electron rich, meaning it's going to react faster as a diene. And then this is an electron withdrawing group via resonance, because I see that pi bond with an electronegative atom. So my resonance structure is going to put a positive charge on this carbon number 5. So that means I need to connect carbon 1 to carbon 5, because I need to make my nucleophile meet my electrophile. The most negative charge attacks the most positive charge. So my curved arrows start at carbon number 1, or sorry, the pi bond between 1 and 2, and go to carbon 5. So I'm going to erase those resonance arrows. I'm just going to write with resonance, get a positive charge here, because I don't actually want the resonance structure, right? That's not the major resonance contributor. It's just helping me see where my reactive site is, right? So I go, that bond goes from the pi, or the arrow goes from the pi bond between 1 and 2 to carbon atom number 5. So that means that I went from 1 to 5. So now that pi bond between 5 and 6 is going to come over and attack carbon number 4. And then that pi bond pushes over. Or if you go to draw the transition state, then you'd want it flipped over. We get the double or dotted lines everywhere. And also a common mistake that was made on the last exam was people were doing dashes instead of dotted lines in the transition state. Remember that those are two different things. The dash, that's indicating stereochemistry. The transition state is a straight up dotted line, right? It's showing that that bond is just partially made or broken. It's not a stereochemistry. It is a partial bond. So yes, either you are flipping it over, so this is 1, 2, 3, 4, and then 6, 5 if you continue in the counterclockwise. But I need to indicate that 1 and 5 are being made, 4 and 6 is being made. So that's what tells me that is not my correct product, where I have the ester right next to the R group. The correct product, the only product, is the one where you have the ester farther away from the R group. Because we got to still pay attention to the nucleophilic site, the electrophilic site, and then make them meet. That's where the key bond happens. All right. Are there any questions about that? All right. And since this molecule, or these molecules, they're not symmetrical, unlike before. You know, when it was symmetrical, I told you it didn't matter if you went clockwise or counterclockwise. Like, it didn't matter where you started. For this one, it does matter. These are the only correct arrows for this reaction. These are the only right mechanism arrows, because we start at the most nucleophilic site and go to the most electrophilic site, and then everything else is a result of that, right? So these are the only correct mechanism arrows with these starting materials, because electronics are now important and it's not symmetrical. If it is symmetrical, it doesn't matter, because it's the same thing whether you go either direction. Here, it does matter, because I have a nucleophilic side and an electrophilic side, and I gotta make them meet. Okay, Try number 3. Right? Is the structure on the left or the right going to be your diene? On the right, that is my diene, because again, it's the 2 alkenes. That's where I get 2 carbon-carbon double bonds. So the thing on the right is my diene. So what's that make the structure on my left? Dienophile. And that's again good. This will react quickly because this dienophile has electron withdrawing groups pulling the electron density away from the pi bond, right? Because you get the pi bond with an electronegative atom next door, so that pulls electron density away from the reactive carbons. Now, since they're both symmetrical, my curved arrows don't matter. I'm going to keep numbering my diene 1, 2, 3, 4 first. You don't have to. I just do to keep it consistent. And then again, because it's symmetrical, it doesn't actually matter which way you go. So just to prove the point, I'll go this way for the first time. Oops. Actually have my pi bond go to the carbon. There we go. So again, I'm making a 6-membered ring. If I number it based on the relative locations here, so I get that 6-membered ring, then, I didn't actually number it in the same way that I did though. Whoops. Because I went clockwise, 1, 2, 4, 5, 6. Yeah, so since I did 1, 2, going number 2 to the right, I gotta do number 2 to the right. Well, I didn't have to, but I'm trying to stay consistent. So that's where I'm seeing that that pi bond is being made between 2 and 3. I don't have anything else attached to 1, 2, 3, or 4. So 1, 2, 3, and 4 just are good. Off of 5 and 6, though, I get this 5-membered ring. And everything else would just come along for the ride. So I just draw that as is, it comes in, and we get a bicycle. Cool? Does that make sense? All right. So now, number 4 is our retrosynthesis. So now that's the product. I want to know, draw your original diene and dienophile that had to come from that, or that had to make that. Think of what bonds have to be made or broken. What did all of the Diels-Alders make? Have a key functional group to identify the bonds that have to be made in the process, and then pull them apart. Bless you. Most students are unhappy about the thing they have to draw, if that makes you feel better. If you draw it and you're like, that's weird, probably drawn the right product. All right, which ring are we going to break? The 4, 6, or 5? The 6. because the Diels-Alder always made this 6-membered ring. So that's what's telling me I'm going to break the 6-membered ring in the middle, right? So I know that this is the one that has to be broken. That's the one that's, or rather, that's the one that's formed in the reaction because we make the 6-membered rings. Now, if I think about my diene and dienophile, if I think about that general reaction, it was 1, 2, 3, 4, 5, 6. I see that alkene in the cyclohexene, that is carbons 2 and 3 of my diene, right? So that tells me that's 2, that's 3. So then I continue my numbers out from there to see that I'm breaking the 1 and 6 and the 4 and 5. Those are the bonds that are being made because you go from that pi bond, go 1 carbon out on each side, that is your original diene. So if you were to think about like pushing the bonds around, you could imagine that we're like doing that same cyclization but in reverse, so that I'm now ending up with a 4-membered ring that has 2 terminal alkenes sticking out like that, which is usually the thing that everyone's like, that doesn't look cool. And yeah, it's weird, but it's going to react quickly with the Diels-Alder. Reacts quickly because it's stuck in this like transformation, like the arms sticking out. So these are my original starting materials. My diene is the 4-membered ring. My dienophile is the 5-membered ring. Does that process make sense? The key thing is remembering in the Diels-Alder, we're making that cyclohexene. So it's the 6-membered ring with the pi bond. That's the one that we make. And then we're going to go either side of the alkene to identify what was originally my diene. And then the other bit is my dienophile. Okay. So I told you part of the power of this reaction is we're going to be able to control our stereochemistry, right? I told you that we can get up to 4 contiguous stereocenters, get up to 4 chiral atoms all next door to each other. So to control the stereochemistry, we're going to do it with, depending on our substitution patterns, of our diene and dienophile. For the dienophile, that's usually the easier side to recognize, because for the dienophile, your stereochemistry will be retained. So what that means is if you start with a cis alkene, you start as a cis dienophile, you get cis substitution in the ring, right? So when I look at this, if I do 1, 2, 3, 4, 5, 6, I see that this is a cis alkene because my 2 groups are on the same side, so it's cis. So I get that 6-membered ring. With the alkene between 2 and 3. And then when I go to have my esters drawn in, because it was cis to start, it needs to be cis at the end. So I'm going to get 2 wedges and 2 dashes. And I intentionally made one of them the methyl ester and the other one the ethyl ester so that it wasn't symmetrical. so that they actually are still chiral centers, right? Because if it was the same thing, then they wouldn't be, no, they still would be chiral atoms. Yeah, the molecule wouldn't be chiral because it would be meso, but you would still have chiral centers. But anyway, so I need to have the cis relationship. That's the key thing. Oops. So you get both the original cis plus the enantiomer. If you start with a trans dienophile, your trans alkene, then, oh, stop moving. Then you get a trans ring. So then I'm now going to get these substituents on opposite sides instead of the same side. So if they start on opposite sides, they end on opposite sides. Where one is a wedge, the other is a dash, plus the enantiomer. Start with a cis dienophile, you get cis ring. Trans dienophile, trans ring. When we consider the stereochemistry of our diene, it must be S-cis. So because the fact that it's not a normal alkene, we're going to describe it based on the stereochemistry relative to the sigma bond. That S is saying sigma. Why we use an S instead of the Greek letter sigma, I don't know, since sigma is a letter, but we don't. I don't know. We say S-cis. So the idea is, when I look at that sigma bond between my dienes, or between my alkenes, if my alkenes are on the same side, then it is S-cis. It's not cis. Cis on its own, CIS on its own is talking about one alkene on its own, the stereochemistry of one alkene. S-cis is talking about a relationship of two alkenes relative to that central sigma bond. All right? So when they're on opposite sides, then it's S-trans, because now the alkenes are on opposite sides of that sigma bond. The S-trans is the more stable version. But S-trans is not able to react. S-cis is less stable because now I have my big groups pointing at each other. It's more congested, more sterically encumbered, but required to do the Diels-Alder. Only S-cis can do the Diels-Alder, which should kind of make sense. So if I imagine this stick, whatever, this thing, if this is the dienophile, all right, and I am the diene. Actually, can I have someone come hold one side of the stick? Cool, thank you. Ooh, careful. All right, hold it up for me, please. Just, yep, beautiful. All right, so this is my dienophile. I am the diene. So my arms, these are the two alkenes hanging out here. If I am S-trans, so my hands are pointing in opposite directions, right? Like one's behind me, one's in front, then sorry, I'm a little bit too close. So then when I go to react, I can grab the dienophile, but like I can't make the ring because my arm is in the wrong side. I gotta rotate it over. Now I can react. Now I can make that ring, right? So if I'm locked, where I'm like, I'm stuck with my arms out front, I am ready to go. I'm like, yeah, come here, dienophile. Let's make a bond, right? So that we can react right away. So you have to be S-cis. You must have your two alkenes pointing in the same direction to do that reaction, to actually reach out and grab that dienophile. Thank you so much. I really appreciate it. Whoops. You must be S-cis in order to do the Diels-Alder, okay? If you are stuck in that S-cis, if you are locked S-cis, you're gonna react really quickly. If you're locked in the S-trans, you will never do the Diels-Alder because you can't get your arm around, right? So as long as you have this free rotation, so as long as you're not a ring, then we're gonna be able to, although you want to exist in S-trans, you will rotate, become the S-cis, and then react. You will swing that arm around so that then you can grab, because it happens all in one go. It's not stepwise. It's not one hand grabs and then you rotate. It is you rotate your arm around and then you reach out and grab. All right, so when I look at this first example, I need to rotate my diene in order to get it into the S-cis conformation. As soon as it becomes S-cis, now it can react with my dienophile. It must rotate. This next reaction, am I going to be able to form a product? Or I guess, why is there no reaction? It's locked S-trans. Right? I'm in this ring. Remember that when we're in a ring, I don't have free rotation anymore. That's why we can have cis and trans with rings, right? That's why we have that facial selectivity where you have top face and a bottom face. You can't rotate this. So I'm locked S-trans. If I'm locked S-trans, I can't do the Diels-Alder. There is no reaction. Or if you're told to rank how fast or slow it is the slowest possible because it doesn't happen. So this is no reaction. Very slow in terms of my diene reactivity because it won't do anything. There is no reaction. Okay. Any questions about my stereochemistry? Yes. So in a mechanism, yes, I would want you to, you wouldn't have to show the arrow, but I want you to show that you need the S-cis. So if you, this like rotation showing that you're making a conformational isomer, this I don't care about, but I want you to redraw the structure as S-cis. Yeah. So in a mechanism, you don't need this arrow. If you draw the arrow, it always helps me to be like, I'm rotating this, so it like, I do that as like a reminder to myself of like what's happening here. But yeah, you need to draw S-cis if you're doing the mechanism of the Diels-Alder. Any other questions? If we are forming a bicycle, so the bicycle is where we have our two rings being formed, where we have these shared carbons, right? We're getting these bridge heads, And then we have our relative bridges as you go between each bridge head, if we remember way back when in chapter, whatever that was, 4? Whatever it was. When we're trying to think of the bridge that we are forming, this is going to be happening if I'm imagining I started with a cyclic dienophile or a cyclic diene. It could be either way. That makes the bridges, the bicycles, sorry. So when I look at this, if I'm trying to think of my original diene and dienophile, I start at the alkene and I go 1 carbon over. This is my original diene, right? That's the original diene. So then when I think of my dienophile, it can't be 1 carbon, right? Because the dienophile had to be an alkene. So I know that this is not the bond, like I'm not breaking these bonds. I have to break these bonds. Also, this is a 5-membered ring. It needs to be a 6-membered ring. Ooh, come back. So these were my original diene and dienophile. Oh, we are out of time. All right. So I do recommend starting the Diels-Alder homework. We're almost done with the Diels-Alder. We haven't, the last thing that we need to do is radicals, which we will do after Thanksgiving break. Well, we'll finish this first, and then we'll do radicals. Yeah, do start the homework though. It'll help you save time so that you're not trying to rush everything right after Thanksgiving break. All right, have a wonderful break. Do spend time, relax. I know I just told you to do homework, but like, do also take this time to rest and recharge. I can tell you're all getting really burned out. We're going into finals. I don't want you to be sick during the final exam. So it really is important to spend some time taking care of yourself, take care of your health, relax a little bit this break. Have a wonderful day. Hey, what's up? One last thing, if you requested a regrade, if you need your exam and you requested a regrade, send me an email and I will scan your exam and email it to you so that you can have it to start the extra credit over break. So if you haven't received a comment on Canvas yet, then send me an email and I will email you the copy. If you receive the comment on Canvas, then your exam is ready and please just pick it up. Okay, cool, thank you.